Hello everyone, my name is Jackson Harris. Today I'm going to be talking about the bomb calorimeter experiment that my group is going to be doing next week.
Arrow key.
The arrow key's not working.
Okay.
Okay, there it is. Yeah, so basically stuff we'll be talking about in theory, what is a bomb calorimeter, how does it work, and what we'll be solving for. Some applications about how the properties that we're getting will be used in industries, and then procedure of the experiment, how it's going to be run, and then just some of the required calculations and estimated results. So this is a graphic of a bomb calorimeter. Basically, its purpose is to measure the amount of energy released during a combustion reaction. And the way it works is the center steel part, called the bomb, will have a combustion reaction inside of that, and that will heat up the water around it through convection, and then the temperature difference will be measured to estimate its heat of combustion. So first in the center, it has the crucible with the sample fuel in it, with an ignition wire that goes through that. When setting that up, it's important to make sure that the ignition wire doesn't touch the crucible itself, because if it does, it'll use that as a ground and the circuit won't be able to be completed and ignite the fuel. Next, there's the outer bomb, which will interface with the water jacket on the outside to heat it up during the reaction. There's also a thermometer. We'll be using a thermocouple connected to a laptop to get a curve of the heat increase after the combustion as opposed to just before and after. And then there's the stir, which moves the water around to make sure that it's all uniform and there's a consistent temperature across the whole thing. There's also the oxygen supply. Ours is a little bit different. We'll be using an oxygen tank to pressurize it with ideally pure oxygen to make sure that the fuel has an oxidizer to ignite, and then for it to have a consistent gas inside of the crucible, or inside of the bomb. We'll be using this equation, first law of thermodynamics, Q equals mCv delta T. And using that, we know the properties of the steel and the water on the outside, and once we have the change in temperature, we'll be able to solve for Q and then get the heat of combustion for the sample. Some applications for this, basically anything that uses combustion in engines like the aerospace industry, the automotive industry, and then military weapons such as bombs or things like that. It's important to know how much energy will be released during combustion, just to make sure that your equipment can handle the forces necessary and how big the explosion will be. So for the basics of bomb preparation, first we'll be cutting 10 centimeters of nichrome wire. That will be the ignition wire that will touch the fuel. Our first one will be the benzoic acid fuel test. That'll be our control sample, just because we know the properties of that. And then we'll be using a separate fuel sample that we don't know the details of. That needs to be less than 1 grams of fuel, just to make sure that the bomb itself can handle the forces involved. There'll be a milliliter of water inside the bomb. The purpose of that is to make sure that when the combustion happens, that all the ash and soot will be concentrated on that, so there's not a big mess. After all that's in there, we'll cycle through pressurizing, depressurizing the bomb with the oxygen tank. When you have straight air in there, it's not going to be a consistent reaction because you don't know what elements are involved, but if it's straight oxygen, it's repeatable, and you can be sure that you'll get the same answer every time. And then the final pressure should be at 30 atmospheres. And then for the water jacket, we use 2 kilograms of water. That's just enough to cover the whole bomb and have a good amount of convection and heat transfer, just to make sure there's a good interface with that. And then it has to be within 5 degrees of room temperature. This is to make sure that we aren't measuring the natural heating or cooling of the liquid as opposed to the room temperature. We can just have a straight difference between the water and before and after the combustion. Then for calculations, we'll be using same formula as earlier. The mCv of the calorimeter, that's constant, so we can use that for the mass of steel times its CV plus the mass of water times its CV to get 9.84 kilojoules per kilogram Kelvin. And then using that, we assume that the change in temperature is 1 Kelvin, the mass of the benzoic acid is 0.001 kilograms or 1 gram. And using that, we can solve the earlier equation for Q, which is 9.84 kilojoules per kilogram Kelvin, and then we solve for CV of the benzoic acid at roughly 9,840 kilojoules per kilogram. Some reasons this is probably not right is because it's measuring the heat of combustion of the whole thing, whereas this is just a specific heat. And something important to note, when doing the reaction, the nichrome wire will ignite and have impact in the combustion. So once it's depressurized and everything's taken apart, you need to make sure to measure the wire just to see how much energy was lost through that. And then it also could have been wrong. Some sources of error would be wrong estimates of the CV of the different materials and or the mass of the water and the steel. So, any questions?